All right, this one's one of my favorite problems in this review set. It's on page 182. It's number 54. And the point of this problem is really getting at what it takes to be continuous and what it takes to be differentiable. So let's look at this function. F of x equals the sine of 2x, but this is a piecewise function. It's only the sine of 2x for values of x that are less than or equal to 0. And it's m times x for x greater than 0. M is just some constant, but we don't know what. It could be a half, it could be pi, it could be 5, it could be negative 100. We don't know. M is some constant number. And the question is, for what values of m is f of x continuous? Now they're only asking about continuity at x equals 0. But we ought to be able to think about what it would be for other values of x too. If it's not x equals 0, if it's x equals some negative number, then we are purely in this branch, and this branch down here makes no difference to us at all. If we're at x equals negative 1 or negative 2 or negative 0.001, we are in this branch and we're not touching this branch at all. And so then all we have to think is, when is the sine function not continuous? Well, if you think about the graph of the sine function, sine is the one that looks like this. And so if we're looking at negative values of x, we're talking about this section in the left. That's always continuous. It goes on forever and ever and ever back to the left. It's always continuous. So that thing's always going to be continuous. What about this? M times x. Well, m is just a number. So maybe this is 1x, maybe it's 2x, maybe it's 5x. Maybe it's negative 3x or negative 1/4 x. No matter what it is, a constant times x, well, think mx plus b. That's just a slope of a line with a y-intercept of 0, because it's plus 0 over here. So that graph might go like this. It might come down like this if m is a negative number. It might be more steep. That's supposed to go right through the origin. There we go. And of course the line would go back here too, but we're talking about the piece that's for positive values of x. So we can really ignore anything to the left. Okay, so when is this thing going to be continuous? At x equals some positive number. If it's x equals 1 or 3 or 5 or 7, well, that's just a straight line. It's always continuous. The only point of continuity that we need to even worry about is where we switch from one branch to the other. In order for it to be continuous at the place where we switch, remember the definition of continuity is that the limit as we approach, in this case x equals 0, whatever x value we're looking at, as we approach from the left, and the limit as we approach from the right have to be equal to each other, and they have to be equal to the actual function at x equals 0. So, okay, at x equals 0, we're in this top branch. It's the one that's got the equal sign. We are not down here. So f of 0 is the sine of 2 times 0. 2 times 0 is 0. The sine of 0 is 0. Okay. Over here, the limit as we approach from the left. As we approach from the left, we're in negative numbers. We're still in this top branch. And as x gets closer and closer to 0, we're getting closer and closer to the sign of 0, which is still 0. So those two, obviously, going to be the same. It's this one that we need to think about. The limit as we approach from the right. Well, that means we're in this branch. As we come in from the right, it's m times some small number, small positive number, 0.1, 0.01, 0.001, etc. As we get smaller and smaller, m times that number gets smaller and smaller, and it's going to be essentially m times 0, which is 0. So all three, both limits and the value of the actual function, all equal 0, then this thing is definitely continuous. Did it matter what value of m we put in? It didn't. Even if this was 100 million times a number that's getting infinitely small, it's still approaching 0. So for what value of m is f of x continuous? All values of m. M can be any real number, and we're still going to get continuity. M is a member of the real numbers. M is in the real numbers. Okay, there we go. So, great. Part B says, for what values of m is f of x differentiable at x equals 0? All right, well, let's think about that. Let's clear off a little room here. Okay, when is it differentiable? Well, remember, differentiability implies continuity. So it has to be continuous. It can't be differentiable if it's not continuous. So we've got to make sure it's continuous. Hey, lucky us. We just saw that it was continuous no matter what value of m we put in there. So we're okay here. As long as m is a real number, then it is continuous. All right, then in order for it to be differentiable at x equals 0, the left-hand derivative and the right-hand derivative have to be the same. In other words, the derivative as we approach 0 from the left and the derivative as we come in from the right need to be the same. So the derivative of the sine of 2x evaluated at x equals 0 needs to be the same as the derivative of mx evaluated at x equals 0. If we were doing this at any x value besides 0, we wouldn't need to mess with this. But 0 is the spot where it switches from one branch to another. So that's why we care. If we were looking at x equals 1, we would just be looking at that branch and the sine of 2x wouldn't matter to us at all. But because both branches touch x equals 0, we got to make sure that it works from both sides and that they're equal to each other. Okay, so let's do the easy one first. The derivative of some constant m times x is just m times the derivative of x. The derivative of x is 1, so it's m. Plug x equals 0 into that. Well, there's no x's, so it's still m. In order to get the derivative of the sine of 2x, we're going to have to chain rule this. F is sine G is 2x, f prime is cosine, G prime is 2, so f prime of G is going to be the cosine of 2x times G prime is 2. We're evaluating this at x equals 0. 2 times 0 is 0. The cosine of 0 is 1. 2 times 1 is 2. What value of m makes f of x differentiable? M equals 2. The sine of 2x has a slope of 2 as it approaches x equals 0. So we need to have a slope of 2 on the other side in order for it to be differentiable. Otherwise we would have a corner there.